Good afternoon, everybody. Awesome. So just wanted to get a little bit of energy on the room. My name is Amit Shah. I'll be talking about the new EC2 instances that we launched recently. And then I've got with me two technical experts, David Desroches and Amir Hakmi, who are going to talk about the parallel file system and how to use storage optimized instances to build them. Before I go further, just a show of hand, are you guys already using storage optimized instances like the i3, i3en, D2, D3? Show of hands. Okay, awesome. So that's good to know. So let me ask you a question. How many instances did we launch yesterday? New instances, storage instances did we launch yesterday? There are three options, 1, 2, and 3. So anybody for 1, how many instances did we launch yesterday? Okay, nobody for 1. For 2 instances? No. 3. Okay, 1, 2. Two people. Okay, so the answer is that we launched 2 instances yesterday and announced 1 more. So we announced 3, but physically launched 2 instances. And I'm going to get into those details and then give you all the data about what are these instances going to look like and how they can help you with your workloads. Okay, the agenda is fairly simple. We're going to talk about the storage optimized instances, just a quick overview of what we do, what we offer today, then talk about the new instances, and then once I complete that, then my friends here are going to talk about the parallel file system. So let me start with general overview of what is the storage optimized family. Basically, the storage optimized instances are designed to support a variety of workload which are more I/O intensive. So workloads that need access to local capacity. And here we offer 2 choices. One is where you have the NVMe-based SSD locally available, which is through the I-instance family, the i3 and the i3en. And then the other choice is the HDD-based instances, where you need a larger capacity, significantly lower dollar per terabyte, and those instances are the D family instances. So when we talk about the I instances, the 2 major instances that we have today are the i3 and the i3en, and they are optimized for medium to large data sets for workloads such as NoSQL, traditional databases, indexing and search, distributed file system, who typically want higher storage performance and lower latency. On the other side, the D family instances, they are optimized for workloads with very large data sets and can benefit from high sequential throughput and very low dollar per terabyte of storage. So again, depending upon what your workload is and what kind of storage you need, we have all these choices available to you today. So if I have to click down into, hey, what are these i3 and the i3en instances, then this is a good overview of it. So i3 instance is a good balance of compute and high storage performance. So really designed to help workloads with small to medium-sized data sets who require a lot of compute performance and a good amount of storage performance. They enable up to 15 terabyte of storage with 64 vCPUs. On the other side, i3en instances, they are optimized for high storage density. So they pack in 60 terabytes of NVMe storage with up to 96 vCPUs. So again, depending upon a workload, you can choose one of them. If I switch gears to the HDD-based instance, we've got 2 offerings here, predominant offering that we launched last year around this time frame, the D3 and the D3en. D3 is a good combination of compute and HDD storage. So D3, if you're already using an existing instance called D2, so D3 is an easy migration from D2, so offers the same kind of capabilities, except for the fact that it enables up to 30% more compute performance, 2.5x the network throughput, and up to 27% lower dollar per terabyte. So again, easy migration from D2, but offering all of these goodies. It packs in up to 32 vCPUs with 48 terabyte of HDD storage. On the flip side, D3EN is all about very high density of hard disk. So D3EN packs in 336 terabyte of hard disk with 48 vCPUs, and it is about 80% dollar per terabyte cheaper compared to the existing D2 instance. So significantly cheaper HSD capacity that you get with the D3EN instances. Okay, so if we step back, we support, in terms of your workload and the CPU architecture it requires, we support the Intel x86-based Broadwell CPU with the i3 instance. With the i3EN today, we support Skylake and Cascade Lake CPUs. That said, we have been getting a lot of customer interest with Graviton, and we already have Graviton instances with local HDD, local SSD, the Graviton disk variants, and customers have been using it for their high-performance cache file use cases, and they've been really happy with it. So these customers also have this additional use cases like databases, indexing, and search workload, where they need the higher compute performance and higher storage performance. And that is how the whole idea of enabling a NVMe SSD storage instance with Graviton came across. So yesterday, we launched 2 new instances, IM4GN and IS4GN, featuring the Graviton CPU and packing in NVMe SSD. So again, the idea is to give you more choices. We also announced i4i. i4i is an Intel Ice Lake-based CPU storage instance. So between x86, which is i3, i3EN, i4i, and the new Graviton instances, the idea is that we want to offer you enough choices such that you can optimize your workload and get the best possible price performance for your workload. All of this, the fact that, for us to help you improve your price performance, not only we want to give you more choices of instances, which we are, but we also want to constantly innovate on your behalf. And the Nitro system is a classic example of how we innovate on behalf of our customers. The Nitro system is a unique combination of building blocks that we can bring it together in unique ways such that we can deploy and deliver new instances with flexibility of compute, storage, memory, and network. So it really helps us drive fast-paced innovation and deliver value back to our customers. Now, the innovation does not just stop here. Obviously, you have heard about Graviton. I'm assuming you guys heard about Graviton 3 announcement that we made yesterday. It was a big announcement, 25% more performance, CPU performance than the prior generation, so significant performance improvement. So again, this is another example of AWS driving innovation. Then we've got Inferentia, which will deliver 70% lower cost per inference, and Trainium, which can deliver 60% better price performance for machine learning training as compared to the GPU instances. All of these are very good examples of how we are driving innovation on your behalf to help you lower the cost. In the 6 years, that journey has not slowed us down, meaning we are just continuing to do that innovation, and the next big innovation that we are driving is with storage, the AWS Nitro SSD. So let me get you some more details as to, hey, what really, so when I was talking with customers about what is their storage workload, what is it that what they would desire from the storage workloads, 3 themes came out of that. Number 1 was they wanted us to reduce the tail latency, or I should say the latency variability. Because for real-time workloads, reduction in tail latency directly had an impact to the workload performance. So that was the number 1 ask, that if we can further tighten up the latency band. The second feedback that I consistently heard from customers was, hey, they would want us to prioritize in reducing the overall latency of the storage platform. So rather than focusing on reducing empty drive or peak numbers, or I should say rather than focusing on improving the empty drive or peak IOPS number, they really wanted us to figure out ways to reduce the average latency of the SSD. So that was an interesting feedback. And then the third thing was that they want to continue to improve our reliability and quality of storage offering. So with the scale of Amazon Cloud and the fact that there are numerous workloads that run on the cloud, it gave us a good understanding of how the applications, how the databases, operating systems, they take advantage of this block storage. And all of that knowledge really helped us, and the feedback from our customers really helped us drive our next innovation, which is the Nitro SSD. Nitro SSD, first of all, the 3 new instances that I talked about, IM4GN, IS4GEN, and I4I, all the 3 instances are going to be exclusively built using Nitro SSD. So the storage capacity that you see in those instances will be based on this new SSD. Nitro SSD is custom built by AWS and helps significantly improve the performance of IO-intensive workload by lowering the latency by up to 60%, and reducing the latency variability by up to 75% compared to the i3 instances. So as you can see, significant reduction in latency and the tail latency. So which is a big advantage, something that our customers really desire. The other thing that it did is that the fact that we could bring a significant amount of innovation with hardware, firmware, and software, it really helped us drive consistent I/O performance and also improve the reliability of the overall storage subsystem. Oops, I should have. Okay, sorry about that. So building our own devices gave us the opportunity to design an operational telemetry, add more hooks for debuggability and diagnostic, and helped us enable ways to deploy firmware at cloud speed at the cloud scale. So all of these things really improves our operational posture, improves our reliability, and improves our customer experience. So that's another big thing that really happens because of the fact that we own the whole storage system all the way from the nitty-gritty of the hardware, firmware, all the way to the software layer. Everything is owned by us, which really helps us deliver all this innovation back to our customers and create unique value. The Nitro SSD is also encrypted with AES-256 ephemeral keys, which means that these keys get destroyed every time you stop or terminate the instance, destroying the data. And this is our way of ensuring that your data always stays secure. So now let me click down into the new instance itself. So the first instance that we launched yesterday is IM4GN. And IM4GN is a Graviton2 based storage optimized instance, delivering the best price performance for a storage optimized instance, optimized for workloads with medium data sets, which can benefit from high compute performance and high network throughput. Okay? Now, IM4GN is more comparable to i3 instance or the upcoming i4I instance, delivering up to 40% better price performance and up to 44% lower dollar per terabyte compared to the i3 instances. These instances pack in 30 terabytes of Nitro SSD and enable up to 100 gigabit of network throughput. They will come in 6 sizes with up to 64 vCPUs and is optimized for workloads that can map to 4 gigabyte of memory per vCPU. So again, significantly better price performance and 44% reduction in dollar per terabyte compared to i3, Graviton based. The second instance that we launched yesterday was the IS4GEN. IS4GEN is a Graviton2 based storage optimized instance, delivering the lowest dollar per terabyte for NVMe SSD in EC2, optimized for workloads with large data sets, which can benefit from high storage density per vCPU. So these instances, IS4GEN, are comparable to the existing i3EN instances. So if you're already using i3EN, then you definitely want to check out IS4GEN. So these instances are comparable to i3EN, delivering up to 15% lower dollar per terabyte compared to i3EN, and up to 48% higher compute performance compared to i3EN. These instances also pack in 30 terabytes of Nitro SSD with up to 50 gigabytes of storage, and 50 gigabits per second of network throughput. There are going to be 6 sizes with IS4GEN with up to 32 vCPUs, and is optimized for workloads that map to 6 gigabyte of memory per vCPU. Okay. We have been testing these instances with some of our customers, and the customers who have tested these instances, they are super excited for us to launch this because of the price performance benefits that they're seeing. And I'm just quoting couple of customers here. Obviously, if you go on our website, there are more customer testimonials that you can find there, and a lot more information you can find there. Splunk, they tested their C, C++ Blaze indexing and search workload. And they mapped all of that from the existing i3, i3N to the IM4GN, IS4GN based clusters. And after doing that mapping, they were able to complete that mapping in about 2 weeks. And after completing the mapping, they saw a 50% reduction in their search time, which points to a significant price performance improvement and lower TCO. So they're very, very excited with the new Graviton instances. Sprinklr, on the other side, they mapped their Java-based search workload to the Graviton-based instances, and they saw their query time reduced by up to 50%. And this enabled them to see up to 40% price performance improvement. So these companies are very excited to transition their workload to the new Graviton-based instances. Let me also talk a little bit about the upcoming instance that we announced yesterday, the i4i instance. i4i is an storage optimized instance based on Intel Ice Lake processor and delivers the highest storage performance, optimized for workloads with small to medium data sets, which can benefit from high compute performance and highest compute performance per terabyte. These instances are, think of these instances as a easy migration path from i3. So if you're already using an i3 instance, this i4i instance should enable you a easy migration to the new instance. They deliver up to 50%, 55% higher compute performance compared to i3. So significantly higher compute performance. They pack in 30 terabyte of Nitro SSDs and 75 gigabit of network throughput. They will come in 7 sizes with up to 128 vCPUs and 1 terabyte of memory. So these instances were announced yesterday, and they will be launching in the upcoming weeks. Okay, so just to summarize where we are, IM4GN, the instance that we launched yesterday, best price performance for the storage optimized family and up to 44% lower cost per terabyte in EC2. i4i, which is a comparable instance to IM4GN, high storage performance and highest compute performance per terabyte. IS4GEN gives you the lowest cost per NVMe storage, lowest cost per terabyte of NVMe storage in EC2. So this is the cheapest NVMe capacity that you can get on EC2. And then i3EN is the highest instance NVMe storage. So they pack in 60 terabyte of NVMe storage within the family. So highest instance NVMe storage in EC2. The idea of all of these instances is that we want to make sure that we give you the best possible portfolio and the best possible choices to help you reduce your TCO. And it's not only about giving you choices of all these instances, but the fact that we're going to continue to innovate with the Nitro system and the Nitro SSD to help you improve your price performance for your storage optimized workload. So that said, at this point, I'm going to now invite my friend David, and who's going to talk about parallel file systems.
Thanks, Sumit. Hi, my name is David Roche. I am an ISV solutions architect based out of Boston. So Amit just went through kind of all of the different instances that live inside of the storage optimized family. And we thought it might be fun to talk about a use case where we can actually leverage some of these things to do, well, lots of different kinds of workloads. So I'm going to go through a little bit of an introduction to what parallel file systems are, a little bit about how they work. If you know those things already, feel free to take a nap or daydream, whatever makes sense. And then we'll get into the actual implementation of it, how you would put this thing in place and use it using these instance types. So a parallel file system is basically a way of creating a file system that spans lots and lots of nodes in order to give you a highly performant, highly scalable way of accessing data sets. And we usually use these for big workloads that are kind of job-oriented more than anything else. So you've got a big data set of something. We'll talk about some of the industries in a moment. And with that something, you run a lot of compute against it, come up with some sort of result for it, and that gets stored elsewhere. So it's generally batch-oriented, but again, it can be used for lots of other things. We typically see this in HPC environments. Again, I'll show you the industries that these live in a minute, but I've also seen them in media environments, stuff like that, as we're doing things like transcoding of large amounts of data. There's a bunch of different examples of these. The most common that you've probably heard of is Lustre, but there's others like BGFS, OrangeFS, PBFS, and so forth. They all kind of have their own things that they bring to the table that make them unique, but each thing kind of has its own user base and feature set that go into it. So in the world, there are lots of places where big data sets make sense. And it could be because you're doing research of some kind. So I work with a number of genomics-based customers where they have large data sets of proteins, et cetera, that they're doing work against to try to generate candidates for medications, these kind of things, treatments. Other people do it in financial services. So they'll have big sets of things that they run compute against to try to figure out what trends are in the market and so forth. Oil and gas for exploration. Things like climate and geosciences to have an understanding of where things are moving from climate perspectives and so forth. So there's kind of a lot of different places where these things tend to show up. But again, they sort of tend to follow that HPC sort of world. When we talk to customers about these kinds of use cases, there's some things that they're concerned about that we want to try to address with this kind of solution. So the first is that you'll notice a word jump out in that first line, and that word is ephemeral. So what we're going to show you when we actually build this thing out is that this is designed to be temporary. Temporary can have a lot of different meanings, but what we mean by this is that it's job-oriented. So we're going to have some amount of data. We import that data into the parallel file system. We run a job against that data, and then when we're done, the output of that goes somewhere persistent, and we get rid of the cluster that we built. So the reason that we do this is because, like most things in AWS, we want it to be very elastic. We want to make it so that you can use things as you need, and then when you're done, you can get rid of them and only pay for that period of time that you're using them. The second piece is predictable low latency. Because we're talking about directly attached storage on these instances themselves, you can control where those things live. So where they live in the AZ, et cetera. And so you know that you're going to get a specific set of characteristics regardless of what you're doing. Now the third bit is, I should mention that there are managed versions of these that are out there. So we have some ourselves, we'll talk about in a little bit. But the idea is that you want to have control. People that use these tend to have some amount of religion towards them. There's some feature in them that appeals to them, that they want to be able to tune, et cetera. So by having this thing running on an instance where you have control over everything inside of that instance, you're able to make changes and tune things exactly how it makes sense for you. So if you have bigger files, it might work one way. If you have lots and lots of small files, it might work another. Because we're talking about something that's ephemeral, it has to be automated. So we'll talk a little bit about a CloudFormation template to make this happen. So you can spin these things up and spin them back down very, very easily without having to go through all of the effort of configuring all the different individual pieces. And then finally, there's a lot of instance types that work with this, and you choose what your price and performance looks like. So if you don't need a lot of speed from an I/O perspective, you can do things that are based on hard drives. If you need lots of speed, you do things based on NVMe, and you choose what your CPU characteristics look like as a direct result as well. All right, so let's talk about the basics of parallel file systems. The idea is that you're taking servers, instances, that have local drives attached to them, and you're aggregating them together into something that looks like a file system to the clients that access it. One thing that's really important to understand with this is that the clients that are accessing it generally are going to use something custom. This isn't going to present NFS or some like SMB or something of that nature. The custom clients are used because they have to understand where to get files and where to put files. We'll talk about that in a moment. Again, you can adjust what the speed and storage ratios look like by choosing certain instance types, certain hard drive types, et cetera. You're going to make the decision of how this thing is going to work. The other interesting thing about parallel file systems is that they scale very, very linearly. So if you need more storage, you basically add nodes to it, and it expands out on the fly as you're using it. So the key piece of parallel files, parallel file system is that it stripes data across multiple servers. So if you put a file into a parallel file system, that data exists on multiple servers simultaneously. So when the client retrieves that data, it's going to be pulling it from those servers individually. Thus, you wind up with a capacity that actually exceeds what an individual server could feed you if it was just giving you the entirety of the file itself. That's kind of the whole purpose behind this. The other piece is when you're talking about parallel file systems, we're generally talking about lots and lots of compute resources that are hitting this thing at the same time. So all of those things can be hitting these and pulling file segments from all the different components within the parallel file system at the same time. So you end up with performance that, again, works in a very linear fashion. So the way that these work is it's a distributed architecture, as I mentioned, based on a bunch of different nodes. And it's generally comprised of 3 different types. You end up with a management setup, which is exactly what it sounds like. It's just there to keep track of where everything is. There's a metadata server or group of servers. And the metadata servers are there to basically direct the clients as to where to read and where to write files. So there's a lookup that's done to the metadata server, and then the client kind of goes off to all the other servers that it needs to in order to retrieve the data. And then finally, there's the storage nodes, and the storage nodes are exactly what they sound like. It's where the files and file pieces live in this environment. Each of these pieces can scale independently. So depending on what your workload looks like, you may have lots and lots of storage servers and very few metadata servers, or if you're looking at lots of different small files, for example, you might have a ton of metadata servers and maybe not quite as many storage servers. Again, it's a flexible kind of architecture based on what your needs are. So again, the client is going to go off to the metadata server, figure out where things live, and it issues read and write requests to the individual servers that it chooses. Most of these have some way of doing archival, of doing tiering, of doing replication. So there are ways to make it so that, while we're talking about an ephemeral kind of notion, there are ways to make this a persistent kind of storage mechanism as well that will be tolerant of drive failures, node failures, et cetera. The last piece is kind of important, which is that depending on which parallel file system you use, there may be some kernel elements. And this makes things interesting from a management perspective. They do this for performance reasons because they don't have to run in user space, but it means that things are very tightly coupled to the kernel. So whenever you have to do something like an upgrade, it becomes a little bit of an interesting problem to solve from a management perspective. All right, so with that, I'm going to hand it off to Amir.
Thanks, David. You guys can hear me, right? All right, cool. Hey, everybody. Amir Hakmi, Solutions Architect, based in the Northeast region. So David talked to us about parallel file system in general and kind of walked us through the basic architecture and how we can potentially set it up on EC2 instances. But what I'm going to do right now is just kind of give you an example, which is PGFS, and it's one of the kind of parallel file system that's available out there for a lot of our customers to be used today. Just before I start, anybody here familiar with PGFS? We've got 1, 2, probably 3. Okay, good. Now, what about Power File System in general? Okay, good. All right, so PGFS, again, it's a Power File System that was developed by Fraunhofer Center back in 2007, and it was really developed with a strong focus on performance. But they also kind of wanted to make it easy to set up, to manage, and to install, because David already mentioned this, Power File Systems are kind of notoriously known to be complex enough to be managed, and that's because, for example, the whole kernel thing and the dependencies. So PGFS like kind of wanted to keep this Power File System simple enough, but also they kind of kept in mind that it has to work across many different workloads. And when I'm talking about performance-oriented workloads, things like HPC, AI and deep learning, oil and gas, and those are just few to mention here. One of the cool things that I like about PGFS is that actually support storage pool, or what we call it the multi-tiering, which I will kind of double click on this on my next slide. So let me actually move on to my next slide. So here's just like a basic architecture to kind of show you how you can actually deploy PGFS on EC2. So what I'm showing here is just a cluster that consists of 6 different servers. So technically you can create a cluster based on performance and the storage, so you can actually choose between different instances, and Emmet already walked us through the different instances that we offer today. So you can actually pick and choose and say, okay, I need to create a cluster based on, for example, what I'm showing here is the i3EN and the D3EN. And since I mentioned that PGFS is kind of known to, or one of the features to have this kind of multi-tiering, you can actually, for example, choose the i3EN to be your tier 1, and that is going to give you higher performance. And then, for example, choose the D3EN instance type, and that's going to be your tier 2. And then you can actually, like if you have a specific workload that needs high performance, you can definitely, based on the directory pattern, you can say, okay, I need this workload to run on these kind of particular instances, and that's going to be your tier 1, higher performance. If you don't care about performance, you just need something to kind of handle the workload, then eventually your tier 2, which is going to give you a kind of a lower cost with lower performance. And one thing here to also to mention, one of the core kind of features of PGFS, it's not only distributing the storage, you're actually distributing the storage and the metadata. And here you will notice that I have a desk on every node that actually is working as a metadata desk. And the reason PGFS is doing that is technically we need to make sure that users are getting the kind of the lowest kind of latency possible when they're doing specific things like directory lookups. So by distributing your metadata desk across as many nodes as possible, you can bring down that latency to its minimum, and that will kind of give you higher performance overall. And of course, you can have the rest of the desk to be kind of formatted to be kind of the storage desks across the many nodes, which is distributed. One thing also to mention that you need to have a management node. This node can be a standalone, or you can actually just have one of the storage nodes to kind of act as the management node. Now, here's again, this is just a basic kind of architecture. Definitely you can scale the capacity based on your workload. Here we're showing only 6 servers, but if your workload requires thousands of nodes, definitely that's something that you can consider, and PGFS should be able to handle that. So David mentioned earlier that the idea behind using the ephemeral kind of desks and the whole kind of the i3EN and the i4 instance type is just to kind of have these job-oriented workloads, meaning that customer may have a workload that needs to run for a couple of hours or maybe a couple of days, a couple of weeks, and they no longer need to have the cluster up and running. So in this case, you need to have some kind of automation to make sure that you have a consistent deployment for your PGFS cluster. And this for that reason, actually, we've created a CloudFormation template, and this template is available in our public GitHub repository and AWS samples repository, which I'm going to share the link toward the end. But what this CloudFormation template will do, we'll deploy a similar architecture to what I showed you earlier, meaning that you will have a cluster consist of 6 servers, and then you have the client, of course, that is going to access all these servers. And since this is going to be publicly accessible, we made sure that this deployment is going to be as secure as possible. So we have all the network dependencies. So the CloudFormation will take care of all that, as you can see here in the diagram, where we have the cluster and all its nodes living in a private subnet, and then we have the Bastion host and the public subnet. Then this way, if you want to administer the cluster, you can just do that through the Bastion host. Now, it's cool to deploy things yourself, but again, the parallel file systems are complex, and sometimes it's going to be time-consuming process. So we have options. A lot of our third-party partners, they use AWS Marketplace, and that's where they actually put their offering. PGFS is one example. So you have PGFS by ThinkParquet. It's available in Marketplace, and that's not the only one. We have other options as well on our Marketplace, like, for example, the Xcalar Cloud, and many others actually out there listed. So to kind of summarize all this, I know we kind of start with talking about EC2 instances, and we're talking about parallel file system, and then PGFS. So the idea here is just we wanted to tell you that you have options when it comes to AWS. If you want to build something yourself, you're confident, you have the right resources, and you have a lot of custom requirement, then definitely you can use EC2 instances. You can run your parallel file system, whether it's PGFS, whether it's something else, definitely you can use EC2 instances. And that's why we are working hard to make sure that we offer you or we give you the right instance type and size. So for example, you can pick and choose between, I mentioned this earlier, the i3, now you have the IM4, you have the IS4, and then you have the i4 as well. And those give you like kind of different options. And since, for example, PGFS give you the multi-tiering, you can mix and choose between these kind of many different options to fit your need. But if you don't want to do that, you just need to have a parallel file system to do the job for you, then definitely we offer FSx for Lustre, which probably a lot of you guys are aware. It's our managed services, and you can definitely use that as an alternative. And I mentioned earlier, if none of these two works for you, you have other requirements, third-party offering on our marketplace is also an option. So with that, I think we're going to wrap it up. Here are the links for a blog post that me and David actually worked together that talks about how to deploy PGFS step by step. And if you want to check out the CloudFormation template, it's actually available in our GitHub repository, so make sure you check it out. Again, this CloudFormation template is just going to do the basic setup for a PGFS cluster. It's not meant to be for a production workload in any way. It's just to give you an idea on how you can actually set up a cluster on EC2 instances and how you can use it. With that, I think we're going to wrap it up. And for Q&A, thank you very much. Questions? Feel free. We currently don't have, David, do we have any performance? No, we don't, actually.
Sorry, your question was, do we have any performance benchmarking that we can share? So can you clarify, are you talking about parallel file system or are you talking about instances? So latency improvement, as I said, that in terms of percentages, it is up to 60% lower latency and up to 75% lower latency variability. Just to give you an example, we typically don't publish numbers because latency for storage devices is something very, very peculiar to how you're going to test it with the FIO benchmarks and what kind of conditioning, prior conditioning you're doing. So the results would vary. There are a lot of test conditions, and it's very difficult to do an apples to apples comparison because a lot of vendors and they all have their different ways of publishing these numbers. And the empty drive or the peak drive numbers, we feel that they are not a very good way of measuring it because they do not represent real-time workloads. That said, if you're aware of a benchmark called ACT, it is from Aerospike. So what Aerospike ACT tool does is that it measures how much throughput you can deliver for a given latency consistently, right? So it's a measure of throughput consistency for a given latency. And on that particular measure, the Nitro SSD is going to be 4x of what the SSD performance you get on the i3 instance. So if you run that ACT benchmark, which we feel is very close to what customers would really want to see because of throughput consistency, then you will see up to 4x improvement for that one. So if you run, as I said, we don't publish these numbers, but if you happen to run the ACT benchmark on your i3 instance and you run that same benchmark on IM4GN, you should see a 4x improvement. It's a fairly straightforward test that you can run. That is a great question. So yes, that is correct. Even throughput can be workload specific because again, the kind of read-write mix that you have can really be very, very different. So right now, we only publish the 100% read and the 100% write. Obviously, the customer workloads are very, very different. So I do agree with that, meaning what we can do is if you're highly interested, then I would love to maybe talk to you in a separate call where I can probably share a lot more details about what this is, SSD instances can offer with the Nitro SSD. Okay, any other questions? Okay, so the question is that because Nitro SSD is brand new, how is the operating system going to figure out, and then is it going to be a standard NVMe device or not? So the answer to the question is that it is a standard NVMe device. So from an application perspective and how you initiate your instance and how you deploy your workload, absolutely nothing changes. So the way you would work with i3 and i3N, it will work exactly the same. The magic really happens between the Nitro system and the Nitro SSD where that tight integration happens. So that is where not only we can virtually figure out, okay, what is the capacity that an instance needs to, like we have 30 terabyte, but if you're choosing something like a 4XL, then you're probably only getting 1/4 the capacity, right? So all of that virtualization of storage happens within the Nitro system, and the whole performance consistency and lower latency is all the work that happens between the Nitro system and the Nitro SSD. All of that is completely hidden from what you would see at an operating system level. Any other questions? Okay, if not, then we can call it a wrap. Thank you, guys.
Thank you.